Today we're talking about graphing pH during titrations. And we don't only do titrations with acid-base reactions, but they are one of the most common. So we do want to talk about these pH curves that we can create during a titration. On a pH curve, we have pH along the y-axis, we have the volume of the titrant added along the x-axis. And what this graph is showing is it's showing how much the pH is changing as we add more and more of the titrant. And with all titrations, we always want the equivalence point and the endpoint to be as close to each other as possible. So we can actually use a pH curve to try and estimate where the equivalence point will be. We can always find the equivalence point because it will be the most vertical region of the graph. What ends up happening during an acid-base reaction that we'll get into much more next year in Chemistry 30 is the first bit doesn't actually change the pH that much. The pH is only going to rapidly change once we get ourselves very close to completely neutralizing the reaction. And then even just a little bit, just a couple drops of the titrant can be enough to change the pH dramatically. Here, going all the way from about a pH of 4 to about a pH of 11. That's a very dramatic shift that probably was only driven by maybe a half dozen drops of titrant. So a single drop of titrant can actually get pH to shift quite dramatically. And we can use that to our advantage. Because what we'll do to try and get the equivalence point and the endpoint close to each other is we're going to try and pick an acid-base indicator that we add to the sample that will change color close to the equivalence point. So if it's equivalence point is 7, a strong acid and a strong base reacting, the obvious one is litmus, because litmus changes color from 6 to 8, but we can use it with other colors as well. We can also use this to actually analyze the contents of an unknown solution. Like we can determine if it's monoprotic or polyprotic. Monoprotic acids will only be able to react with a base once, so we end up with this one equivalence point, one vertical region. But if we have more than one hydrogen, if it's a polyprotic acid, then you will end up with more than one equivalence point, or if it's a polyprotic base. So here we're taking the base, sodium carbonate, and we're neutralizing it with hydrochloric acid. And while the equivalence points aren't nearly as vertical, you can see that there are actually 2 of them here, which makes sense because this can act as a base twice in the presence of the strong acid. This is saying that we have a polyprotic base. There we go. We have a polyprotic base. Specifically, we have a diprotic base because there's 2 reactions. So that's an important type of analysis that we can do with titration. What we also see here is we also see why methyl orange got selected for the second color change, because methyl orange changes color from yellow at about a pH of 5 to red at about a pH of 3. And the equivalence point is just under a pH of 4 on this curve. So we're using the methyl orange because only a drop or 2 is going to make it shift past that color change range, because we see it goes here from here, where the graph is nearly vertical. So just a drop will be enough to change the color of the methyl orange from yellow to red, shift it through its entire range, telling the chemist that they need to close the burette. And that's basically what we do for choosing any acid-base indicator during titration. We want to look at what we're expecting the pH to be at the equivalence point, and we will talk a bit more about how to predict that in Chemistry 30, and then select a acid-base indicator that's going to match that equivalence point. And because the vertical region is so dramatic, there's actually really three indicators that we really commonly use. We commonly use litmus, we commonly use phenolphthalein, and we commonly use methyl orange. This would be for when we expect a neutral, a basic, or an acidic equivalence point, respectively. So we're always looking for where is that color change going to be? Do we expect the color change to happen close to 7, above 7, or below 7? And then just picking an appropriate acid-base indicator to tell us when that reaction's finished.